plan for today, is to cover vector spaces. We're going to look at different types of vectors and what we can do with those vectors. So, vector spaces. Let's begin. Okay. So a few definitions. A vector is an ordered n-tuple of elements of the field. All that means is we have some numbers, and these numbers are in a specific order. So this is not equal to this, for example. Even though it's the same numbers, they're ordered. A vector steals the moon. Crazy. What? You can see me? Okay. Right, so yeah, this is a vector. And then we have the definition of something called a field. So a field is a set F which has two operations, plus and times, or addition and multiplication, such that for all pairs of elements, so for all A and B in F, the following hold. We're going to go through what all of these are, and then we'll think of some examples of fields. Okay, so additive identity, multiplicative identity, associativity, commutativity, additive inverse, multiplicative inverse, and distributivity of multiplication over addition. So let's start with these two. Can anyone tell me what an additive identity is? What does that mean? Zero. Okay. Yeah, so zero is an example of an additive identity. And the idea is any number, if we add zero, it will just result in that number. It doesn't change that number. Okay, so what about a multiplicative identity? Or what's an example of that? 1. Good, yeah. So if we times any number by 1, it's still just n. And so this is those two identities. We call this plus 0, or this times 1, neutral elements, which just means that it keeps this a neutral. It doesn't affect that a, essentially. I just need to change some settings. So yeah, that's additive and multiplicative identities. It's just, it doesn't change the actual result. Okay, and then we have associativity and commutativity. Can anyone tell me what associativity means? A few of us are typing. The order of operations of the same precedence. A plus B equals B plus A. Not quite. So commutativity is, yeah, that second one. A plus B equals B plus A. Whereas associativity is about the order of the operators not mattering. So associativity is this, for example. Whether we do this plus first and then add this, or whether we do this plus first and then add this, is the same as doing this and this. Yeah, so right associativity is an example of that. So it's essentially saying order of the operators doesn't matter. Or the order in which we apply the operators doesn't matter, as long as they're all the same operator. So that's associativity. Commutativity is the exact same, but instead of the order of the operators not mattering, this is about the order of the operands. So, whereas here the order of this plus, doing this first and then adding C, whereas doing this first and then adding A doesn't make a difference to the result. Commutativity is about actually changing the order of the operands, so maybe flipping this A and B. Does that make sense? Isn't associativity also just within the same yeah, so these operators have to be the same precedence, essentially. Yeah, so this would actually also apply if we had minus, but in the definition of a field, we just care about addition and multiplication. Okay, that's associativity and commutativity. Additive inverse. Can anyone give me... So a field is just a set, some set, which has these two operations, and this holds for every possible pair of numbers in that set. So we've looked at these four. Additive inverse. Can anyone tell me what this means? Okay, we'll go through it. So Additive inverse is just, if we take any number, let's say n, yeah, minus. So if we take any number and we add some other number in the set, we can reach 0. So the definition of additive inverse is just that there exists some number in f where we can add it to get 0. So additive inverse. So here, for example, if we have a and we can also get minus a in that set, then we can reach 0. So this would be our additive inverse, this minus a. Multiplicative inverse is the same, but instead of adding, we times, and our goal is to get 1 here. So multiplicative inverse says if we have a term, there exists another term we can multiply it by to get 1. Obviously, this is assuming a is not equal to 0, because this would be 1 over a, and we can't divide by 0. Yeah, so the reciprocal, essentially. For example, if we had 5, what would be the multiplicative inverse of 5? 0.2, yeah. So 0.2, or a fifth, and these would both result in 1. So this would be the multiplicative inverse. It's dollar signs. Okay. Cool. Right. I'll just keep that example there. So, moving on. Our final sort of condition for a vector to be, for a vector space to be a field, or a set to be a field, is distributivity of multiplication over plus. And all this means is, oh no. Okay, all this means is when we expand something like this out, the times is stickier than the plus. That's how I like to imagine it. So this would become a times b plus a times c. And so the idea is we sort of implicitly do this, where we prioritize the timesing over the plus, and we get ab plus ac. So this distributivity has to be met. This condition has to be met for a set to be a valid field. So those are the sort of, you can almost imagine this as precedence in a way, where the times takes precedence over the plus. So those are the conditions for something to be a valid field. Okay, so let V be any set of vectors. So that will just be a set of maybe 1, 2, 4, 5. This will just look something like this. So imagine this is V. And F is any field. So let's just say F equals the natural numbers. Okay. Actually, let's not use that right now. Okay, let's just say we don't know F yet. Okay, so V, a set of vectors, is said to be a vector space over the field F if these conditions hold. So these are quite similar to the ones we've seen, but this is about vector spaces, not fields. So commutativity of vector addition. This is just the same as commutativity, where order doesn't matter. But if we try and add two vectors, it will always equal the same as just adding them the other way around. The order of operands doesn't matter again. Okay, associativity. So what does this mean again? What's associativity of vector addition? So all that means is if we do a plus b plus c, but we do this first, it will have the same result as doing a plus b first and then plussing the c. So that's what associativity tells us. Okay. Additive identity is just that every vector has another vector in the V set of vectors that makes 0. Existence of additive inverse. Oh no, sorry. Additive identity is just that there exists a vector which results in the same vector. Yeah, sure. So I'll do it. A field is just any set F with two operations, plus and times, where for all pairs of numbers in that set, these conditions hold. I'll just grab a quick screenshot of this and send it. Cool. Okay. Yeah, so here we are. Okay, so existence of additive identity just tells us there exists some vector, so this might be 0, 0, for example. And if we add any vector to this, it will just result in that same vector. It doesn't actually change the vector. So this would be a neutral element, this 0, 0 vector. Additive inverse just tells us that there exists some other vector in the vector space which results in a 0 vector. Okay. So this is where it starts to get slightly different to just field definitions. So associativity of scalar multiplication. Can anyone think of what this means? Associativity of scalar multiplication. I'll give you a moment and then I'll go through it. I'm going to copy these to a new page just because we're running out of space. Okay. So, oh, I see someone's typing. Okay, so we know associativity is talking about the order of operators or operands. Which one? Which one's associativity talking about? So associativity is always about the order of operands, whereas commutativity is talking about the order of actual... Sorry, associativity is always about the order of the operators, whereas commutativity is about the order of the operands. And we saw that up here, where associativity is the operators, so how we're actually applying those pluses or timeses, whereas commutativity is the order of the actual operands, so maybe swapping the order in which we provide it to the operator. So associativity is about the order of operands. Of scalar multiplication, so the scalar multiplication of two vectors is just when we have some vector, let's say 1, 2, and we have some scalar like this, and so that would result in this. So associativity of scalar multiplication tells us whether we do 4 times this vector, for example, or whether we do I could think about how I write this. Okay, or whether we do this times 4, this doesn't make a difference. So the order of the actual operands, whether we apply this first, or I'm going to rewrite this as okay. So let's say we had that. Okay, so this is talking about whether if we have scalars involved, still that same rule about associativity applies here. So whether we times a vector by a scalar first and then another scalar, or we times it by the other scalar first and then the vector, or even if we times these two scalars together and did 8 times a half, all of these, 8 times 1, 2, all of these are equal. And so the order of operands doesn't matter. Okay, distributivity of scalar sums just tells us if we have something like, yeah, exactly. So 6, this rule tells us that if we have something like 4 plus 2, and we want to times that by a vector, then this sum would distribute out. So it would become 4 times 1, 2, plus 2 times 1, 2. So we're distributing this addition into these sort of two numbers. Distributivity of vector sums is the exact same, but here we have something like 1, 2 plus 3, 4 times, say, 5 would be equal to 1, 2 times 5 plus 3, 4 times 5. So the idea is we can just expand it out. Whenever we see distributivity, imagine how we'd expand it out. And so this has to be possible for something to be a vector space over a field. Okay, and finally, 8 is nice and simple. Existence of a scalar multiplication identity. So this is just that there exists some scalar value in our vector space V, where if we times it by a vector, we have that same resulting vector. So we have a neutral element in our vector space. do these rules sort of make sense? Are there any questions about any of these in particular? Or anything anyone's unsure of? Cool. Awesome. Okay, so yeah, these are the 8 rules for a vector to be for a set of vectors to constitute as a vector space over a field F. So a vector space is on a field. Yeah, exactly. So for us to have a vector space, there has to be some field involved. Okay, before we move on to the next part, can we think of any examples of let's say, okay, of some valid fields that we could use? So what sets could we write down? Okay, let's just okay. So natural numbers, only thing to consider here is we don't actually have what are we missing with natural numbers? What can't we do there? Yeah, so we don't have an additive inverse. Yeah, and we also don't have a multiplicative inverse. So we can't use natural numbers. We can't use integers. Why? We wouldn't be able to use integers. Yeah, we don't have a as Ollie said, we don't have a mult inverse. We don't have a multiplicative inverse. We do have an additive inverse because for any integer in Z, so for any integer we take out of Z, we know its additive inverse would just be its negative, and the set of integers would, yeah. Okay, and real numbers. Okay, do the conditions meet for real numbers? Let's just pull up our conditions again and see if any of them contradict. So this is the conditions for a field. So we know with real numbers we have additive identities. Yeah, multiplicative, additive inverse. We know we can do associativity and commutativity with numbers from here. Multiplicative inverse, because if some value n is in real, then we know 1 over n is in real because of the definition of real numbers. And distributivity. So this would be the only valid field out of these 3 sets. None of the other sets would work if we wanted to have a vector space over that field. Okay, does that make sense why we can't have natural numbers and why we can't have integers as fields? Okay, cool. Awesome. Okay. And then we were introduced to something called rings. So a ring is just a field, but without multiplicative inverse and commutativity for multiplication. So could you have a field of complex numbers? I wouldn't. With complex numbers, if we go to the field, would it contradict any of these? Any of these sort of... Okay, I'm not too sure about it, but yeah, it would have an additive identity because we can just sort of negate it. Multiplicative identity. If we want to... Does the complex numbers... It's just a real field... Oh, yeah, okay. I guess if it introduces a real and imaginary, then I think we'd be able to. But I'm not too sure on that, so don't quote me on that. Okay, so... Yeah, possibly. Okay. A ring is a field, but we don't have a multiplicative inverse and commutativity for multiplication. So these are the updated rules for a ring. We don't have our commutativity for multiplication, but we still have it for addition. So all this means is, say we do A times B, this might not necessarily be the same as B times A. We can't guarantee that these two are equal or the same result. Whereas we can still guarantee that A plus B equals B plus A. And multiplicative inverses don't exist. Yeah, exactly, like matrices. Where if we times two matrices, say we have a matrix A and a matrix B, that is typically not always the same as B times A. Okay, and then multiplicative inverse, we don't have these anymore. So which one of our sets could we... So we had real numbers, natural numbers, and integers. So which one of these, or which of these would be valid as rings? Let's think back to what was holding us back for some of them, or what conditions we've got rid of that now allow. So up here we said integers aren't a field just because they don't have a multiplicative inverse. But with a ring, that isn't a requirement anymore. So integers would constitute as a ring. Yeah, and real numbers, they'd also constitute as a ring because this is less strict than a field. And if this is a field, then it's definitely a ring. So the only one that's left is natural numbers. And we know this can't be a ring because it contradicts this rule here. We don't have an additive inverse. Okay. Cool. Let's move on. Okay. So the span of a set of vectors is all of the possible vectors that we can obtain as a result of a linear combination of the vectors. So just to recap, a linear combination is where we have some scalars and we times them by the vectors, and we add and we sum those together to get a new vector. So for example, if we had 1, 2 and 3, 4, can anyone tell me a linear combination of these two vectors? Just type one in chat. Linear combinations of these two. Four, 6. Okay. Yeah, so we can obtain 4, 6 by just saying 1a plus 1b. And so these would be our two scalars. This would be our R1 and this would be our R2 on this definition here. So anything where we have these two constants would be a linear combination of these two vectors. As long as R1 and R2 are in the field we defined. So whatever field this vector space is over. So let's say we had these two vectors here. What would be the span of those two vectors? Can anyone write out what would that set look like? If our field is the real numbers, what would be the span of these two vectors? I'll give you guys a moment to think over that. Is it just x, x, x? Not quite. So if we had x, x, x where x is a real, say we had wait, so how are you writing that? Are you saying like it can be anything? Like, would this be in the span? Yeah. So all the components have to be the same. Good. So this set would look something like so x, we'll use your definition, where such that x is in our field, and in this case our fields are, so we can just say where x is in R. So we can't get to any points where it's a vector where not all three are equal. So we can't get to this point with a linear combination of these two, for example. But we can get to 4, 4, 4. We can get to 6.6 recurring, 6.6 recurring, 6.6 recurring. As long as the three components are all the same, it will be in this span. So both of these two would be in the span of 1, 1, 1, 2, 2, 2. Okay. Yeah, so anything times this first vector plus anything times this second vector would be in the span, where A and B are both in the field in this case, real numbers. Where you can get to... Yeah, exactly. A nice sort of graphical way of looking at it is if we have... Say we have a 2D, and we have this vector here. Or actually, let's do this in 3D. I don't know how I'm going to do that in 3D. Okay. Wait, can I draw a line? Okay. Just use your imagination and imagine that this is the z-axis. Yeah. Okay. Right. So, if we had a vector like this and a vector like this, imagine both of these vectors are just in the x and y axis. So, imagine this is something like 10, 2, and this is 5, 8. Okay. And the z component is just 0. So imagine we had these two vectors. The span of these two would only be this plane here of x and y. We wouldn't be able to actually... Yeah, anything that has a non-zero z component we can't reach. Because no matter what scalars we use and times these by and add them, this z component will always be 0. And so we can't actually reach any of the points in the z-axis. It's only where we can reach with a linear combination of, say, vector A and vector B. Does that make sense? In terms of the definition of a span and how we sort of... Okay, cool. Awesome. Right, so a set of vectors, and then a bunch of vectors in some vector space V. So let's just highlight V is some vector space. It forms what we call a basis if the following conditions hold. So the span of all of these vectors that we're looking at is V. So what that means is we can reach anywhere in this vector space. We can get any of these vectors by using a linear combination of these vectors. So we can essentially reach anywhere. I'm just going to add a full stop there. Okay. And the second condition is that all of these vectors have to be linearly independent. So what this means is none of the vectors can be obtained by a linear combination of the other vectors. Or in other words, none of the vectors are redundant. For example, this set of vectors, 1, 1, 2, 2, would not be linearly independent. These would be classed as linearly dependent. Can anyone tell me why? We can make the second... Yeah, exactly. One is a multiple of the other. And so whether this vector's here or not, the span of 1, 1, 2, 2 equals the span of 1, 1. So we don't need one of them. It's useless. Whereas, can anyone tell me two linearly independent vectors? One, 1, and 2, 3. Yeah, exactly. So if we had something like 1, 1 and 2, 3, we can reach any point with a linear combination of these vectors. So what would our any vectors that aren't parallel basically then? Yeah, I believe so. I mean parallel in terms of... Yeah, I think that would work actually. Correct me if I'm wrong, guys. But yeah, so these two are linearly independent and we can reach any point. Just to prove it, by combining these two vectors, what two constants could we use as the coefficients to get to, say, 1000, 1000? So say we want to find some A. Let me copy these to a new page. Okay, so say we want to find some A and some B that we can times by these two vectors to get 1000, 1000. What would this be? Oh, actually, I'm gonna. Yeah, you're right. I'm gonna change that to 1,500. How can we get to 1,500 with the linear combination of these two vectors? Yeah, it's not just parallel. Ollie's right. So say we have three axes. Two of the vectors could be used as a linear combination to get that third vector, but it might not necessarily be parallel. So if we wanted to work something like this out, what could we use? What nice GCSE method could we use? Linear system of equations. Yeah, so yeah, we can solve it simultaneously. So we can say a times 1, which is a, plus b times 2 equals 1,000, and then a times 1 plus 3 times b equals 500. Does anyone have a calculator on hand? Okay, let me know what you get. I'm going to just trust whatever the majority of people say. $2,000A 500 minus 500B. Okay, awesome. So I'm going to trust that's correct. A is 2,000 and B is minus 500. And assuming that these two numbers are both in our field, then this would be valid. This would be a way we can reach the point 1,500 with these two coefficients. Okay, so that's an example of where what linear independence what the span means. If we have these two linearly independent things, would this form a basis over, let's say, would this form a basis over the set of integers? So to form a basis, we need to have the span of the two vectors be z. So the span needs to be this, because we need to be able to reach anywhere in the vector space, and they all have to be linearly independent. So first of all, is the span of these two vectors z raised to 2? Can we reach any tuple of integers or any vector of two integers with a linear combination of these two? So the two conditions checking for is if the span is the vector space, our vector space is just z squared, and we want to check if it's linearly independent. So we know it's linear. We know these two vectors are linearly independent because none of them is a multiple of the other. We can't get this one with this, and we can't get this one with this. So that's ticked off. And we know that we've just proved that we can get to 1,500. Whilst this isn't an exhaustive proof, we can manipulate these values of a and b. And as long as they're in our span, or as long as they're in the set of integers, we can use that to reach any sort of vector we want. And so z squared is actually the same as the span. And so this would form a valid basis because those two conditions are met. Do A and B... so A and B have to be in... if we go back to our definition of a span... so here they've used R1 and R2. We used A and B. They have to be in the field. So whatever field this vector space is over. And for this example's case, I just said the field is integers. If we had a vector space of integers over the field of reals, then they could be real numbers. But since the field's defined as integers here, both of these scalars, or all of the scalars in that we're timesing by the vectors, have to be in that field. Okay. So that's the span. And the last few things I want to cover is that every vector space will have some basis. So R cubed, for example, will have a basis. And every vector space will have at least one. Let me just add that as well. At least one. And the basis of a vector space will always have the same number of vectors. You won't have two bases for the same vector space where one has 3 vectors and one has 2, because that means one of them will be linearly dependent, and so it won't be a valid basis. And this number of vectors in the basis is known as the dimension of a vector space. So for example, here, where we've got 2 vectors, we know that they're linearly independent because one isn't a scalar multiple of the others. And we know that the span of them is the entire vector space. We can reach anywhere in this set of vectors by multiplying these by some scalars and adding the results. And so, because this forms a basis, we can say the dimension of this vector space V is 2, because there's 2 vectors here. So, dimension equals 2. And so this is a 2-dimensional vector space. If we had four different vectors in our basis, it would be a 4-dimensional vector space. Yeah, that's pretty much everything I sort of wanted to cover today. Are there any questions about anything we've looked at? I'll also post the slides soon. Cool. Thanks for coming, guys. Awesome. This is my last lesson, so we're planning some extra stuff at the end of the week. I'll post some stuff in general and some stuff in upcoming about that. But yeah, awesome.